All right. We are, this is the end of week 6, so coming along slowly but surely. I want to make a couple of quick notes. Let me share with you the syllabus so we understand where we're at and what's coming up. This is the 6th week. Okay, you guys had your exam. Now, I haven't finished grading those, so some of you I have, but I'll get that knocked out tonight and tomorrow for sure. And then this weekend, I will open it up so you can go look at your answers and so forth. This month, the 10th, is the last day that you can withdraw yourself without needing a signature or anything like that. Hopefully you don't have to do that, but if you do, that is the last day. And then on the 30th, if you look down here, if you drop the lecture, or excuse me, the lab, for whatever reason, then you must also drop the lecture, according to the departmental policies. So keep that in mind too. So if you drop it the day after, and then you got no problem. You continue the lecture, so FYI. We got the exam number 3, chapter 7 through 9, coming up on the 20th. We should be okay with respect to the chapters. Now the last week, the week of here, but I highlight in yellow, that is the week of Thanksgiving. And what I did is I temporarily moved it Thursday, because we're off, obviously, to move it to a Wednesday lecture. Now, I know some of you can make it, cannot make it, but I think, I'll explain that in a minute, Nick. The way we're going with the chapters, I don't think we're going to need to do that Wednesday. We're ahead, which is good. We'd rather be ahead than behind. So just wait till we get closer to that time period and see how it goes. And if I have to, I will make a Wednesday lecture. I'll be here talking about whatever chapter we're talking about. If you can't make it, that's fine. I do record it. So no problem if you can't make it. Nick, you had a question about commons on the far left. What that is an area for instructors where you can pick up different examples of Canvas courses and so forth. So it's just a resource for instructors. Okay. All right. Any questions? Down. Let me see 1 second. All right. Got one more. Okay, here comes the fun part, chapter 8. Yeah, you can ask a question about the lab, no question. I don't teach the lab, but I'm sure I don't know the answer, I can find out. Go ahead, Nick. You go ahead and unmute yourself. Okay, that'll be fine too. All right, so chapter 8. Chapter 8 deals with a big old fancy word called nomenclature. Basically, all that means is name that compound. We give you a compound formula, from the formula, give that name. Or vice versa, we can give you a name and then work backwards to determine what the formula is, okay? And I've already begun kind of introducing you to nomenclature and naming of these compounds as we've been progressing. And now we're starting to put everything together. We talked about the elements. From there, we talked about the ions that are created by loss or gain of electrons. And now we're going to start putting these elements, or these elements, be it ionic compounds or covalent compounds, to actually make compounds. The next step after this would be to take these compounds we start putting together and start reacting with each other. Okay, so anyway, we have been talking about the simple names for the atoms. For example, you know, Na is sodium, Ne is neon. Okay, way back when I said, hey, learn the first 20, and then we have a few more to be familiar with. We'll be using more as we progress, but here's some more. Ba is barium, Co, lowercase o is cobalt, I is iodine, Cu is copper, Fe is iron, Pb is lead, Hg is mercury, and Ag is silver. Sometimes there's a confusion there, the Hg and the Ag. Hg again is mercury, Ag is silver. Au is gold, Zn is zinc, Sn, you're probably familiar with this, maybe not know it, but check the packaging in your toothpaste. You're probably brushing your teeth with a stannous fluoride. Sn, its name could be either stannous or tin, Tin. Then Sr for strontium, Ni for nickel, Br for bromine, Cr for haven't seen your moment, chromium thing. And Mn. Mn could be confusing too because we have a Mg, which is magnesium, and Mn is manganese, okay? And then Cd, which is cadmium. So be familiar with these. Now, to refresh your memory with respect to the types of compounds, ionic compounds, you got to grasp this concept here, okay? Because it's going to help you definitely down the road here. Any ionic compound that is a combination of a metal and a non-metal, okay? That is an ionic compound. Now, if you forget what a metal is, then I direct you to the periodic table and that stair step. That stair step tells you to the left of the stair step are all the metals, with the exception of hydrogen, which is in the far left, for group 1A. And then everything on the stair step are metalloids, and then in the other side of the metalloids to the right are the non-metals. So be familiar with that so you know who's a metal and who is a non-metal. Covalent compounds, that is, again, a combination of non-metals, so things like carbon and oxygen to give you carbon monoxide, carbon and sulfur, any of the non-metals, okay? The ionic compounds, sodium chloride, good example of ionic compounds. Sodium is the metal, chloride is the non-metal. The other name given for covalent compounds is molecular. They use both at the same time. Now, we went on to talk about the ions and what ions are created depending on whether they're losing or gaining electrons. Okay, so these are monatomic ions, just one atom, like sodium that lost one electron, which, by the way, one of the questions on the exam was to give the electron configuration for sodium ion. And a lot of people were given the electron configuration for the element, the atom. So if you see a question like that down the future, make sure you understand that you're looking at the ion, which tells you that it lost one electron because it's got a +1 charge. So its valence shell is gone and empty. And then chloride, calcium, and so forth. Okay. Now we're going to be using what are called polyatomic ions. And I direct you again to the periodic table because in the far left corner is a listing of the most common polyatomic ions that we'll be utilizing. Now notice that there's two types, just like monatomic. There's a cation and an anion. There's really only one cation that we'll be utilizing, and that is the NH4+. That is called the ammonium. Okay, all the other ones are anions. Now, these are units, they're packets. They stay together. We don't change the subscript. So NO3, for example, the first one in the second column on the right, that is called nitrate. That is the nitrate ion. The next one down is called the nitrite. The only difference between the nitrate and the nitrite is the nitrite has one less oxygen bonded around the nitrogen. But that whole unit has a negative charge. That's why it is called polyatomic ions. Okay. The most common one is down in the bottom left. There's good old baking soda bicarb. All right, so be familiar with these because we'll be using them quite a bit. And so here's again, phosphate, polyatomic ion. Notice a -3 charge. The OH negative, that's called the hydroxide, and the CO3 -2, that is called the carbonate. They're all listed on that table. Now, I've been saying the charge. What is a charge in the ion? Well, we also use the term oxidation state, simply because the oxidation state / charge is true whether it's in an ionic compound and a covalent compound, okay? And so in the ionic compound, there is a true positive charge and a true negative charge. But remember, on the covalent compounds, there is a partial negative or a partial positive depending on the dipole of that bond. And so it's not a true charge, okay? So the term oxidation state encompasses both of them, whether it's ionic or covalent. But the charge remains the same. The oxide ion has a charge of a -2, okay? Or oxidation number of a -2. The oxygen in, say, carbon dioxide, which is covalent, it still has a -2, an oxidation state of a -2. Okay. Now, all the elements, as I told you, have an oxidation state / charge of 0 simply because they have an equal number of protons and an equal number of electrons. Okay. They're in the elemental state. And we know, hopefully by now, that these atoms or these elements, once either gain or lose electrons, it makes them into an ion, be it a cation, which is positive, and a anion, which is negative. Now, the charges or oxidation state have magnitude, meaning depending on how many electrons they lost, 1, 2, or 3, there would be a +1 or +2 or +3. The same is true for the anions. It could be they gain 1 electron, its magnitude would be a -1, gain 2 electrons, -2, etc. Okay. Now, there are some elements that have what's called a fixed oxidation state, a fixed charge. There's only one charge for it. And let me bring back this table. I'll show you my periodic table here in a second. The other ones, the other metals that do not have a fixed charge have a variable charge. For example, here, copper can exist in 1 or 2 states. It can be a +1 charge, which lost 1 electron, or a +2 charge. Now, there are 16 elements that you know or will know 100% of the time their charge, okay? And this is important because when we start to naming these, that's going to be determine how we name them with respect to an additional bit of information that we have to put into the formula to distinguish between the different types of ions, okay? So if we look in group 1, starting from number 3 lithium down to number 87, okay? There's 6 of them. All of them, as you know, have 1 valence electron. All of them are metals. And notice I did not highlight hydrogen. Hydrogen is not a metal. And therefore, they all will lose that 1 valence electron and end up with a +1 charge. Those 6 all, when they become ionic, have a +1 charge. Group 2, next one starting with number 4 down to number 88, those all have 2 valence electrons, and they're all metals, and therefore always 100% of the time would have a +2 charge. So there's 12 right there, 6 in the first column, 6 in the second column. Now there's 4 more that have 100% of the time a specific oxidation state. The first one would be aluminum, number 13. Always will have a +3 charge, 100% of the time. Then diagonally to number 30 is zinc. Zinc always has a +2 charge, always loses 2 electrons, okay? And silver, number 47, will always have a +1 charge, only losing 1 electron. And then moving over next to silver, number 48 is cadmium. That will always have a +2 charge. So there's 16 examples of metals that you know 100% of the time their particular oxidation state, okay? I call them the sweet 16. All the other metals, the oxidation state would vary, and we would have to tell you what oxidation state they're in. For example, up on top in the blue, you see copper 2+, or +2, either way, or copper 1. Well, how do we distinguish between two? Which one we're working? Which one are we working with? Well, what we do is we use Roman numerals and parentheses to tell you what is the oxidation state of those elements that have a variable oxidation state. Therefore, copper, Cu, would have Cu, parentheses, Roman numeral 2, and parentheses. Let me write that real quick. Now, whether I use the symbol or whether I use the name. So copper, in parentheses, Roman numeral 2. Okay? Roman numeral 2. That tells me that I have, one moment, that I'm using copper 2+. Okay? So I could either do it like that with the full name or with the symbol. Okay. Now, don't confuse these Roman numerals with the Roman numerals on top of the group and the periodic table. 2 different types of Roman numerals being used. Okay, this one is used to tell you what is the oxidation state of the metal that you're working with. For example, there's iron, 2 types of iron. There's an iron 2 or +2, and there is a iron 3. Okay, and that's how we distinguish them. They both have the parent name iron, but we have to have a way to distinguish which particular ion you are working with. So again, I repeat, those are the 16. You know 100% of the time what their charge is, which tells you that when you use those 16, you don't use Roman numerals. Okay, no Roman numerals for everybody in group 1 and 2 and those other 4. You just say aluminum, you just say zinc, you say silver, whatever the case may be, but no Roman numerals. The Roman numerals are only for those other than these 16. All right, so let me go back to the slide. And that is what is told here about the variable charge, okay? Now we know that cations lose electrons, and we talked about this at length with respect to the periodic table and the group number for the A, the main elements, the A elements. Group 1A always has a +1, group 2A +2, 3A +3 for the metals, okay? For the metals. And again, I just told you about zinc and cadmium and silver. All the other metals have a variable. It can be from a +1 all the way to a +9. Now, and this again, you're using the Roman numerals to distinguish between which of the variable ions we're talking about. Notice lead can have a +4. And so we will write its name as lead, Roman numeral, parentheses, don't forget the parentheses, IV for +4. Okay, we know about the anions. Anions gain electrons. Okay, we also know that group 5, those nonmetals will have a -3 charge when they gain 3 electrons. Group 6, -2, and group 7, -1. Not only does the periodic table tell you how many electrons it has, but knowing how many electrons it's going to gain can also tell you how many bonds it can actually make. So group 5 can make 3 bonds with something, okay? For example, we did NH3, ammonia. NH3 is in group 5, okay? Group 6 has a -2. That implies that those guys can create additional information here, can create 2 bonds. Good example would be water, H2O. You got oxygen that has 2 bonds of hydrogen on each side. And then finally, the group 7, with needing a -1, gaining 1 electron with a -1 charge. That also tells you that at the most, those halogens can make 1 bond. An example of that would be HCl, hydrochloric acid, the acid that's in your stomach. Hydrogen and chloride, 1 bond. Okay? So not only tells you the charge as far as the group number, but also tell you how many bonds it can make, which can help you when we put instructors together. We know that column 8, they got no oxidation number. They're not going to create an anion. They're not going to lose electrons because the octet is fulfilled and everybody's happy. And helium, obviously, not the octet, but the duet. Now, in dealing with ionic compounds, we're going to begin by learning the formulas and the names for ionic compounds. Now, remember that ionic compounds are made up of ions, and ions have a charge. And when we put them together, their total charge must equal to 0. Now, I gave a general formula a while back to help you out to remember this, and it said that the number of cations plus the number of anions equal 0. Okay, oh, not 0. And so if I have a cation with a +1, I only need an anion with a +1 to come together to write a formula. And if I have a cation with a +2 and my anion each have a -1, that means I need 2 of them, 2 of the negatives to counter the 2 positives from the cation. So they equal to 0. So we're going to run through some examples of these here in a bit. Okay, the polyatomic ions, I mentioned those. Here's that table again. Okay, following your product table. They have specific names. Okay, if we need to add more than one, let's say, for example, for whatever reason, we need more of the nitrate ion. Okay, we need maybe 2 of them or 3 of them or whatever the case may be. We actually, what we do is we put a parenthesis around the whole polyatomic ion, and then we write a subscript to tell us how many of those polyatomic ions we are utilizing. Okay? And that's true for all of these polyatomic ions. We don't separate them. So we wouldn't add any subscript to the nitrogen or the oxygen to increase how many we think we need. We don't do that. We keep the NO3 as it is, NO3 and the acetate and the hydroxide and the cyanide as is. Okay. Okay. So that's what I just stated. It's a single entity. Now, compounds must be neutral. You gotta have enough cations and enough anions to equal 0. So let's take, for example, the first. They give you a combined sodium and nitrogen. Now, they're giving you the element first. They're just giving you the element. Well, we're not combining elements. We're combining the ions of the elements. So you have to know, first of all, what charge you would have. So sodium, we know, is in group 1, so always has a +1. So hence I write sodium +1. The nitrite excuse me, the nitrogen will end up with a -3. We also changed the name when nitrogen becomes the ion, we change the name to nitrite. Okay. And so that being the case, what I do is I make myself, I break it down and I say, okay, I need sodium because it's got a +1, and I need the nitrite, it's got a -3. Okay. And so that means once I know that, I need to figure out how many of each I need to cancel everything out to be 0. Well, I need 3 sodiums. I need 3 sodium ions because each one has a +1 charge to counter the -3 charge of the nitrite. Okay? And so that coefficient I just put up there becomes the subscript for the sodium. And so I can write the formula as so: Na subscript 3 N. And now the name for this would be sodium, because even though the name doesn't change for the metal, but nitrogen, by gaining 3 electrons, now becomes nitride. Okay? Because nitride tells you that is the ion, the ionic form of nitrogen. So its name for that formula is sodium nitrite. Now we're going to be working here with the formulas to give you the name, but also we're going to be doing, given the name, go back and determine the formula. Okay, so let's take this one. All right, we know just from the previous example that sodium has a +1. And so the first thing to do is I take the elements and I write my ions. Okay. Now, what about sulfur? Ionic sulfur, what charge does that have? Anybody know? What charge does sodium, sulfur have once it becomes ionic?
-2.
-2, exactly. -2 because it's in group 6. So I got a -2 charge on the sodium, okay? Okay, now that I got them in ionic form, now I got to put enough of each so they cancel each other out. So here, because I got sodium with a +2, I need 2 sodiums to counter the -2 of the sulfur ion. The sulfur, we change its name once it becomes ionic. The sodium remains sodium. And so the name for the sulfur now is what? Does anybody know what that is?
Sulfide.
That is totally 100% correct. And so that would be the name for this particular compound. The coefficient of the sodium in 2 becomes the subscript that we use to write the formula. And so what we have is the following: Na2S. Okay. And remember, you're always going to have whole numbers. Never end up with half numbers, anything like that. Always whole numbers. Let's try this one. Okay, so I got this one. I got magnesium and oxygen. First thing to do is break it down to the ions. And I know that magnesium is in group 2. And being in group 2, ionic magnesium has a +2 charge. Okay. Oxygen, which is in the same group of sulfur, now has a -2. Okay. Does anybody know the name for the oxygen once it becomes an ion? In this case, an anion.
Oxide.
You got it. And so we got magnesium, the metal name stays the same, and the name for oxygen, once it becomes an ion, is now oxide. Okay, notice that IDE suffix, both on the sulfide and the oxide. And so once I got that set up, I noticed that I got +2 and a -2, excuse me. So they basically can come together as a 1-to-1 because they cancel each other out. So that is the formula for magnesium oxide. Okay. Potassium, okay, well, like I said, I always start with a systematic approach in looking at these problems. Eventually, when you get comfortable with recognizing what ions you're working with, you go directly to the formula. But for right now, break it down. We know that potassium has a +1 charge, okay? And we know phosphorus, you go to the periodic table, phosphorus is in group 5, okay? When it becomes ionic, it's going to pick up 3 electrons. It's non-metal, okay? And so I have those elements, K and P, now written in ionic form. So now I need to add enough of each to cancel the charge. And you can see that potassium with a +1, I need 3 of them. I need 3 potassium +1s to cancel the -3 of the phosphorus. Well, what about the name? Okay, potassium remains the same. What happens to phosphorus?
Never mind, I'm not going to try it.
Give it a shot.
I was going to say phosphate, but
no. Look at that. Look at sulfur. What happened to the last 3 letters?
phosphide.
Okay, so what do you think phosphorus would be? Phosphide. You're right. Yeah, phosphide. I didn't. My bad.
You just said it.
I know. I wasn't paying attention. I had an electronic. What do you call it? Technical error in my earpiece. Phosphide. Phosphide. Okay. So we change. There's a name. Now we got the number of each that we require. We write the formula. Subscript 3 for potassium. Okay. And we have 1P. All right. Let's do one more. Now, a little bit more challenging, but again, break it down. You'll find a lot of these classes and these chemistry classes and problems, they look overwhelming at first, okay? But rely on your basic information and then take a systematic approach at the problem. This is what happens. I worked in the industry for many years. Sometimes you get a problem, you're like, what the heck? Well, you just break it down in pieces, okay? Break it down on what you know, break it down on what you don't know, and then little by little, you're able to come to a place where you need to be. So what is it that we do know? We know that we can take these elements and break them down into the ions. We got to do that first. And so we know that calcium is in group 2, okay? Calcium in group 2, ionic calcium will always have a +2 charge, okay? Now, what about nitrogen? What kind of charge would nitrogen have once it becomes an ion? If you forget, look further up on the slide. What does that tell you up there? A -3, right? Because it is in group 5. It's a non-metal. It's going to gain 3 electrons, okay? So it would have a -3 charge. Now, previously, the other examples, it was pretty straightforward. I can either add 3 of one, one of them had a higher charge, so I just needed to add whatever I needed of the other one. Here, I got a little bit of a different ball game here, okay? I got a +2, and I got a -3 on the other side. Now, how am I going to put these guys together? You might think about it. Well, think about it. What would you do?
We're kind of like the same thing, but you're going to have kind of like what we did before, but we have to do it to both. elements. So like you would have 3 calciums and 2 nitrates.
Yeah, and that's correct, Nathaniel. But you know, think about this way too. What if you needed to? What if I needed to add the fractions 1/4 plus 1/5? What would be the first step I would do if I needed to add those fractions?
Make sure that they have the same denominator.
Exactly. I would need a common denominator here. And here I got the thing that's common. What number would be common between these two?
6.
Exactly. 6. So our common denominator would be 6. So I got to add enough calcium to give me a total of 6. So I would need 3 calcium. Okay. And then I would just need 2 nitrites. Okay, so I put in those numbers up there. That tells me I got enough negatives and enough positives to cancel each other out. Plus those coefficients become the subscript for that particular ion. Okay. Now the other thing too, since I'm here, let's figure out the name. Calcium remains calcium. Nitrogen became nitrite, like we talked about up in the first example. And so I got the name here already in case I need it. It's calcium nitrite. I got the coefficients that I'm going to need because I have a common denominator, in this case, of 6. And so now I can write that formula as 3 calciums and 2 nitrogens. Now there's a little trick here, not a trick, but a little tool that can help you is, if you think about it, if I look at that 2, that 2 was the ionic charge of the cation, right? It was a +2. And if I look at the 3, that was the anion charge of 3. So I basically just flipped the numbers across. They're like a cross multiply kind of thing, and that giving me that particular formula. Okay. So yes, when you get uneven numbers of ions, then I got to find a common number for both negative and the positive, and get enough of each to write the subscript. Okay. Just like trying to find a common denominator when I'm writing or adding or subtracting fractions that are not the same, don't have the same denominator. Okay, so we got aluminum and we have the chloride. And so I unfortunately erased my other examples, but aluminum, we know it's in group 3 and it's a metal, so it's going to lose 3 valent electrons. And the chlorides, it is in group 7. It will have a -1 charge for the ion. So I got to put them together. In this case, I'm going to need 3 anions to cancel out the +3 of the cations. So our formula would be AlCl3, otherwise known as aluminum chloride. Okay. Zinc, similar situation. Zinc is one of the 16, okay? And it always has a +2 charge. The iodine, when it becomes ionic, is in group 7, so it becomes a -1 charge. And therefore, I need 2 iodides to give me for every zinc ion. So zinc iodide is the name here, and that is the formula. Okay, now here's something interesting. So we have Cu Roman numeral 2. What does that mean? What does that Roman numeral number mean to copper? Anybody remember?
All your favorite
No,
Is that a
Re-
+2 charge?
it's a +2 charge. That is correct. Remember, you have 16 elements that you know their ionic charge 100% of the time. And therefore, all the ones up from 1 through 6 are part, all the metals there, all the ionic metals there, the cations, were part of the sweet 16. And so we didn't have to use Roman numerals because they have 100% of the time a known oxidation. It's a constant oxidation number. The other ones, that means that all the other metals, minus the 16, have a variable oxidation number. And you have to be told which one you're working with. So we do that by adding a Roman numeral. So that Roman numeral 2 belongs to copper. And that is telling you that that is a +2 ion that you're working with. Okay, so that Roman numeral says I'm dealing with +2. Okay, and then the oxygen, we know again that it's in group 6. So when it becomes ionic, it's a -2. Okay. Now, since it's a +2, -2, I can simply just put them together and make a simple compound. I'll show you the formula here in a second. But to name this, we have to incorporate the Roman numeral. So the name for Cu is copper. Okay, we continue with the Roman numeral. And then the oxygen is the oxide. So that is the name for this particular example. Copper, Roman numeral 2, oxide. Otherwise, some people just say copper 2 oxide. Okay, and that is the formula right there because we can use them 1 to 1. Now, how would that differ? Because if I use copper 1, okay, if I use copper 1, oxide, that is using Cu, okay, +1 and O -2. Well, that means I need 2 coppers, copper 1s, to counter the -2 of the oxide. So this formula will be Cu subscript 2 and then oxygen. Both of these have the parent name copper oxide. What distinguishing between each other is the Roman numeral, because that tells you what is the oxidation state of the copper that you're using. They used to have names like cupric and cuprous, and that was kind of ambiguous and confusing. And so now the way to name multivariable oxidation state metals is to use the Roman numerals, because unequivocally there's no confusion as far as what cation you're using. Okay. And then here in this example, lead 4, Roman numeral 4 is telling you that you're using lead 4. And then an oxygen. Oxygen again is oxide -2. So that means I need 2 oxides per each lead 4 ion. So the formula is PbO2. Okay. So we started making the compound. So generally what you're going to see is you're given the elements. From the elements, they want you to write a formula for the compound that you're making from those elements. So step 1 is take those elements, convert them to ionic form with the correct charge, okay? And then determine how much of each you need, how many of each element you need, and then that number becomes a subscript when you write the formula. And don't forget, for any metal that's not in the sweet 16, you need Roman numerals to distinguish which element you are working with. All right, so every time you add it, make sure that you check the charges. Everything is going to add up to 0. Now, I gave you a general formula earlier. Total cations plus total of anions equals 0. Okay. Now, you can use this to work backwards. For example, this information. Let's take carbon dioxide. Okay. Can anybody tell me what the oxidation number of carbon is in carbon dioxide? How could I go about figuring that out? Give me 1 second. Give me 1 second. I got to do something real quick. Yeah, think about this one. What is the oxidation number? How can I calculate the oxidation number of carbon in carbon dioxide?
All right. Go ahead and tell me how you would do it then.
I will in just 1 second. You tell me first,
Wouldn't
and
you
then I'll
just,
tell you.
don't you just break it apart the same way you put it together?
Exactly. You keep going, and I'll tell you if you're right.
Oh, okay. Thank you.
You guys
Is that
working?
right though?
What was the number? Yeah, go ahead, Jackie. Go ahead, teach it.
Oh no, you're back. It's okay. Go ahead.
No,
Oh,
no,
you-
go ahead. Go ahead. No, no, go ahead.
Tyler said he was going to.
The best way to learn any subject matter is to teach it. Trust me. So how would you go about to figure out, based on what you know right now with the oxidation numbers, knowing that what would you do to figure out the oxidation number of carbon?
Would you figure out the charge of
Go
it,
ahead.
and
Whoever wants to try it, give it a shot.
would you figure out the charge of it and then break it apart the same way you put it together?
Okay. How would you break it apart? I mean, you're on the right track.
I don't know. I mean,
Okay, well, let me help you out here. Okay, we don't know the oxidation number of carbon, so we're going to break it into like an algebra equation, right? Because remember I said total cations plus anions equals 0. So carbon, we don't know what it is, oxidation number. But what do we know? What do we know about oxygen? What is the oxidation number of oxygen, be it in ionic form or covalent form? The oxidation number will always be the same here.
-2.
What group is it in?
Group 6.
What group is oxygen in?
Group 6.
Okay. And so when it gains 2 electrons, what's its overall charge?
-2.
-2. How many oxygens do we have in carbon dioxide?
2.
2. So what is our total charge? Negative.
-4.
-4? Exactly. Okay. And all that has to equal to 0. Okay. Now, what must carbon be for that to equal to 0?
+4. Oh, yeah, wouldn't it be +4 because it would equal
You,
0?
you got it. Carbon, sulfur, carbon, and that is equal to +4. Okay, so in the form of carbon dioxide, carbon has an oxidation number of +4. Okay, and like I said earlier, you're always going to know the oxidation number of one of the elements. Let's take it one step further. What about carbon monoxide? What do you think the oxidation number of carbon would be there?
+2.
Yeah, exactly. Now you're getting it because it's the same scenario. Okay. And then we know it's a -2 for the oxygens, and that must equal to 0. Okay. Now, to expand that equation a little bit further, because I'm gonna give it to you now because some of your homework they want you to calculate the oxidation number of a compound. Most of the ones we're doing are neutral, but sometimes you get something that's not neutral. Okay, and so earlier I said the number of cations plus the number of anions equal, instead of saying 0, I'm going to say the overall charge of the compound. Okay, and the overall charge for majority, like we've been doing now, has been 0. But you can get a scenario where the overall charge is not 0. Now, let me example. One of the polyatomic ions that we had was SO4, subscript 4, and then -2. Okay, from the polyatomic ions. Unfortunately, I don't have superscript, subscript. That was called the sulfate. Okay, that was a sulfate polyatomic ion. Now, given what I've said, what would be the oxidation number of sulfur? How could I set that problem up? What would I do? Any ideas? Be no different from what we just did.
Separate the sulfur and the oxygen.
You got it. Okay, so we got sulfur plus, what do we know about oxygen? -2. How many do we have?
4.
4.
4. So what's our total negative?
-8.
You got it. All right. What is the overall charge of the ion?
-2.
Okay. Okay, because SO4 -2. You see that from that is a polyatomic ion. Now, can I solve for sulfur here? What would sulfur be? Sulfur equal to what?
Negative. No. +6.
No. You got a -8 on the left side. What do I do to the right side?
Oh, also make.
Well, I got to add negative +8 on the left side to cancel the -8.
Oh, so should it be?
And then I got to add 8 to the right side. Okay. If I add what I do to the left side, I got to do to the right. So if I add a +8 to the left to cancel the 8s, I got to add a +8 to the right. And so now, what does that equal to? That's 6. You got it. So the oxidation state of sulfur in sulfate ion is a +6. Okay. And so that general charge equation up there could be utilized for either a neutral compound and or a charged ion, polyatomic ion compound. Okay. All right. So you hopefully at this point you can see do some practice on some polyatomic ions, and you're always going to know the charges of one of the cation or the anion. Okay, one or the other. For example, let's say I have cobalt Cl4. Okay, cobalt, I won't give you the Roman numeral because I want you to figure that out. But the parent name is cobalt chloride, okay, which is 50% correct as far as naming it. So, but what is the oxidation state of this cobalt? Nobody want to guess? No need to guess. You can work it through like we've been doing all the others. Okay. We got cobalt, right? Plus, what do I know about the chlorides? What
There's
is
a
the charge?
-3 charge.
Well, the chlorides.
-1.
Oh, -1.
Yeah, -1. How many do I have?
4.
4. So that's a -4 there, correct?
Yes.
And the overall charge is 0 in this scenario. So what will be the oxidation state of this cobalt? +4, right?
Yeah.
Okay. And so the name will be cobalt, Roman numeral IV. Oh, forgot my V. Chloride. Okay. And so the point here is that using this general equation, you can calculate the oxidation state of any of the elements as long as you know the oxidation state of one of the partners, because they're all going to equal up to either be 0 if it's a neutral compound, or equal up to the charge of if it's a polyatomic ion like we did the sulfate. All right. Let us move on. All right. So here we're going to be using polyatomic ions to write formulas. Well, same scenario. The only difference is the polyatomic ions. You're going to be given what the charge is. It's there. It's OH negative. So go back to the polyatomic ion tables to refresh your memory what the OH negative is with respect to names. But we do the same scenario. We break down the elements in the magnesium into the ions. So we know that magnesium is in group 2, so it has a +2 charge. And then we're given the hydroxide as a -1 charge. I need 2 of the hydroxides, okay? So already I got the name going because magnesium, the name magnesium stays the same. The only difference is now it is the polyatomic ion that I get from the table to give it the name. So this name would be magnesium hydroxide. I need 2 hydroxides, 2 of the polyatomic ions, which means that I need a parenthesis around the OH. And in the subscript, give me, whoa, to give me that formula. Okay. The polyatomic ion is in parentheses, and since I need 2 of them because it's a -1 charge for each one, okay, I have 2. So the name here would be called magnesium hydroxide. All right, 1 second. All right, so we have this one here. We have potassium and the PO4 -1. That is the polyatomic ion, and it's called phosphate. You can find the name on the table. We know that potassium is in group 1, so each potassium has a +1 charge. We're going to need 3 of them to cancel the -3 of the phosphate. So therefore, its formula is simply K subscript 3 PO4. Now, we don't need a parentheses around the PO4 because it's only one, okay? Only one. If you put a parentheses around it, that's fine. I would accept that. But by convention, it's not necessary to put a parentheses if only one polyatomic ion is needed. Okay, next one. Silver, Ag. Ag is part of the 16. Okay, Ag always has a +1 charge. The SO4 is the sulfate we were talking about earlier, and it has a -2 overall charge. So that means that I need 2 silvers because each silver is a +1 to cancel the 1 sulfate. So its formula is Ag2SO4. Okay. All right. So next one is calcium and NO3 negative. Right? NO3 negative, again, in the polyatomic ion table, that is called the nitrate. It's got a -1 charge. Calcium, we know, hopefully by now, it's in group 2, has a +2 charge. So we're going to need 2 of the nitrates to cancel the +2 of the calcium. And so we put a parentheses around the nitrate and put a subscript 2 to tell us that we need 2 nitrates. And the name here would be called calcium nitrate. Okay.
Okay.
So we got on top magnesium hydroxide, we got potassium phosphate, and silver sulfate. And then this one here, calcium nitrate.
I have a
And
question.
now,
Just to
Sure, go ahead.
just to clarify. So the reason why the parentheses is there is just
Go ahead.
showing that there needs to be 2. Right? That was the whole because
You're-
you needed for
you're-
for number 4.
yeah,
So the reason why there's parentheses is because you need 2 nitrates,
you got it.
and so it makes it to where it doesn't confuse the 3 and the 2 together, kind of thing.
Right, because the polyatomic ions, they stay together. You don't separate them. They're units. Okay, the NO3 is a unit, the SO4 is a unit, the PO4 is a unit, and the hydroxide is a unit. Those are kept together. And if we ever need more than one, we put a parentheses around it to show that we need 2, 3, 4, whatever number we need to counter the charge of the cation.
Okay, thank you.
Okay, so it would be incorrect to take the NO3 and make it N2O6. That creates something that is not the nitrate. Okay.
Okay.
Everyone got that? The parentheses are for the polyatomic ions. Now, taking a look at the number 5. Okay, again, what does the Roman numeral tell you? Does the Roman numeral mean anything?
+2 charge.
We got a +2 charge. Thank you. Okay, so we're working with copper +2. Then the CO3 is the polyatomic ion called the carbonate, and that has a -2. So we can very simply just put them as a 1-to-1 and just write the formula as CO3. if we were going to name that, we would have to write the Roman numerals, and this would be called copper, Roman numeral 2, carbonate. That will be the name for that one. Top one is calcium nitrate, silver sulfate, so forth. Okay. Now, sometimes you're given the name, like copper 2 carbonate, and asked to work backwards to give the formula. And sometimes you're given the formula and you're asked to give the name. Okay. Right, so basically here, when it comes to the polyatomic ions, I'm gonna overemphasize it. When it comes to the polyatomic ions only, okay? You use parentheses to designate that you have 2 or more. If it's a monatomic element like the silver, and we put a subscript through, you don't need parentheses. You just put a 2 or 3 or 4, whatever you need underneath that element. Okay. All right. Let's do this. Let's do one more slide and I think we'll call it. Now, you should be able, at this point, able to write the compound formulas, okay? And then be able to name some of these at this point and distinguish between the ones that have a fixed and a variable charge. And using the Roman numerals when you get to name, when you're naming the compounds. Remember, it's crucial. The 16, no Roman numerals. So if I have sodium chloride, we wouldn't write that as sodium Roman numeral 1 chloride. It would be simply sodium chloride. All right. So anyway, I think we're going to stop it right here. Yeah, keep us in line with the other class. This is where they stop. But some of this I already started to give you, where we're taking the anion and we're changing the name from the INE, for example, in chlorine, and changing it to the IDE once it becomes an ion. Okay. So why don't we stop it here? And I'll give you 7 minutes back for free time. How's that? All right. Any questions? Feel free.
No, thank you.
No? Okay, then.
Thank
Well,
you.
you're quite welcome. You guys have a good weekend. Have a safe weekend out there. And we'll see you on Tuesday.
Got it.
All right.
Thank you. Thank you.
Thank you.
All right, bye.
What's up?
Did you see the screenshot I sent you?
I saw that. I haven't downloaded it yet. What? Let me see.
Oh, I can share my screen. I don't know.
Okay, you can share the screen.
Let me make sure. Okay.
Yeah.
Let me get to
Okay,
it.
I may have to, or let me, hold on, maybe I may have opened, it
Oh,
may have downloaded. It didn't download it. It gave me an error. But let me open up the screen. You should be able to share the screen now. It says disk error for some reason.
desktop. All right. Or wait, let me see. Allow Zoom. I've never done this before, so I don't know. Hold on.
Oh, okay, down in the bottom, you should see a kind of a green button that says share screen.
Yes.
Okay, click that. Then the window pops up. And then you can select whatever screen you're gonna see.
Oh, stop, dude. Let me see. Safari. I don't use MacBooks very often except for this.
I don't use Macs at all.
It's got the webcam, so that's why I'm okay.
Okay, were you able to share it? I mean, Because I opened up the,
What am I doing? Did I break something? No. Let me see. Share screen. Safari?
there could be a multiple screens there. Why don't you open the screen up that you want to see first,
It wants.
then hit the share button, and then select it from.
Ah. Oh. Jeez. Give me a minute, Colin. I have to like do. Oh my god. Well, it's a question about how to make smaller screens. Okay.
How to make s'mores? Is that what you said?
Well, I could smaller screens.
Oh, okay.
So she tricked it. I have a GUI. Well, I don't know the names, but it says enter the data result numbers with the correct significant figures. Hold on, please. And so basically, the mass of the orange juice is only 170 grams.
Okay, let me write this down. The mass, you were measuring something or what?
Yeah, orange juice.
Orange juice, okay.
Yeah.
Okay, and it 170?
Yeah, 170 grams.
170 even?
Yes, yeah, 170 even.
Okay.
The volume of the orange juice is 171 milliliters.
You broke up. I got the 71.
Milliliters. Lowercase m, uppercase L. Shut up.
Yeah.
Okay, so this is where I think I messed up because
You were calculating density?
yes, and I put the density of the orange juice is 0.99.
Okay.
So
Let me get my calculator. 170 divided by 171, and I get 1.994152 whatever. Okay, so let me share my calculator.
I did that, and I also used
You see the calculator?
yeah.
Yeah, I actually just did that today as well.
Okay, so it was 170 grams divided by 171 milliliters. Okay, and so now you're calculating the density, and so now you got to look at your sig figs. So how many sig figs in 170?
It should be 3, shouldn't it? Right?
Well, no, you remember when you divide numbers, when you divide and you multiply, you want to use your answer should have no more sig figs than the number that has the least number of sig figs. So
See.
in that number 170,
Yes. It's only 2.
how many sig figs are there? 2. Okay.
Because I put the answer 0.99.
Yes.
So, and I got partial.
Well, what's it called? I had to go through that same problem, and there was like this hint that it was saying that 0 is a significant number for some reason.
Yeah, there's a hint at the bottom of that question.
Yeah.
For a hint, what's the hint?
Well, that's
Yeah,
what
it was saying like it was given a hint, like given a different type of scenario. If you like subtract these two different numbers and you got 30 milligrams, so it wasn't the actual number, but it was like a little thing, little side note, and it was saying that the 0 is a significant number.
Yeah, you're breaking up. I'm catching.
Is this backwards to you? Wait,
Okay,
we
maybe.
can't
Okay,
see it. It's very hard to see.
Okay, let me have. Is this lab 130, right? Which lab is this? Because I use some of it for my SEC classes. What lab number?
This was.
Mine was
It's just
130.
yeah, lab 130 density lab.
Density? Okay, give me a second. And let me search through my stuff here real quick, because like I said, I do use some of the labs.
Is this backwards to you?
No, it's
Uh,
not.
Yeah, so that hint is like, okay, so wait.
Oh, there you go.
So that's our hint. But then I got
Okay. Here's what she's doing. Did you subtract to get any of these numbers, the 170 and the 171?
One minute. I actually have it right here. I have the.
Okay, because if you subtracted
Yeah.
that number,
Yeah, because she gave us.
I see where you're going. Okay.
With the
Now, when
cylinder.
you have, so one of these numbers you subtracted, and what happens, remember, when you subtract or add numbers, you answer with the least significant figures, okay? But then if you have to take that number and then you have to divide it, then what you do, let me see if I can give you an example. Let me pull it up. So that explains why, because I thought they just gave you 170.
Yeah, no, she gave us like one with the cylinder, and after
Yeah, okay,
towards the liquid.
I got you. And so, let me do this. And so you subtracted something, let's say, I'm gonna try to do this. 150 minus 1.5. Okay, I'm subtracting these numbers here. Okay. Now, when I do that, I get 150 minus 1.5. I get that is equal to 148. 148.5.
Yeah.
Okay. Now then I'm going to take this number for whatever reason, and then I'm going to divide it by, I don't know, let's say 1.5. Okay. Okay. Well, so we have two mathematical steps here. So in the first is a subtraction. And so here we keep track of the decimal places, right? Remember that? Okay. But we're going to divide that number. So we give the full number, but then we mark where the number would end if we were to just report this number. If we were to report this number, it would be 148. Would you agree? If we were just subtracting that number? Oh, 149.
Actually, I've got the numbers if you want to.
Yeah, the actual numbers that you used?
Yeah, because
Okay,
I use the cam scan.
okay.
All right, so
Go ahead.
we were given mass of the graduated cylinder is 123
Okay, you're given 123.
grams. Mass of graduated cylinder plus liquid is 293.
293.
And then they gave us the volume, right? I think was 171 milliliters.
Yeah.
171 on the nose.
Yeah.
So
then
you took, they gave you a mass of 293, okay? And then you subtracted 129,
123.
right?
Yeah, with 293 and then
Okay.
123.
Right. And so here, when you subtracted the number, that zero, you would mark that zero because you're going to take that number and you're going to divide it. Okay, if you were gonna report that answer, I mean, just like that, that has 2 sig figs, okay? Plain 2 sig figs, but you're gonna take that number and you're gonna divide it into a number that has 3 sig figs. So that 0 for the next step would be significant.
Oh.
Okay, so your answer should be in 3 sig figs. And that's
Okay.
what I was trying to show you here in that 150 minus 1.5. If I were going to keep the answer, stop it right there, I would round that number up to 149. Do you see that? Because we're subtracting, okay?
Yeah.
But I'm going to take that number and I'm going to use it to divide the next, do one more, a division the next step. So I would continue to mark it. I marked the 8. That would be where the significant digit would be. Okay, so that would be 3 sig figs at that point. That
Okay, so-
mark represents 3 sig figs because I subtracted and I'm going to divide. And so the next step is I keep that mark there, at 3 sig figs, I keep that mark because of what I did previously with the subtraction, and now I'm going to divide by 1.5. And so my answer would be dividing 3 sig figs over 2 sig figs.
Okay.
Okay? And so in your case, when you subtracted, you got a number of 170. So you have to mark that 0 because that is where you truncated it to get that answer right there. I mean, it just turns out to be 3 sig figs. Let me see if I can.
So basically, since if we kept the 170 and it was just 170 and that's all it was, it would be 2 sig
I
figs.
lost you again.
So
Yeah.
since the 170, if it was just 170 and that was our answer, it would be 2 sig figs.
You
But
got it.
since we divided it, we used it dividing it within another number. We the 0 counts as significant, so it is 3 sig figs.
You got it. Okay.
Okay.
So if you stopped it simply at the math part, then ask you how many sig figs, you will have 2 sig figs. But because you subtracted 2 numbers that are at the one place, the 0, that 0 is marked just like I did up here with the 8. Okay. And so I would have, because I'm going to do the next step with respect to division. So I don't want to truncate 148.5 to 149 because that propagates the error. So I keep all the numbers 148.5, but I mark where I would have truncated. Okay, so I get that mark just tells me if I do a division or a multiplication next step, I got 3 sig figs to work with. So in your case, if I was, let me go back to the text here. In your case where you did 193, 293, okay, and then I'm subtracting 123, and so my answer would be equal to 170, but notice that I'm at the one position as far as decimal places. See, there's no decimal places. So I got to mark that 0 like I did up there. I marked that 0, and that just tells me that I got 3 sig figs here. So whatever I do to next, and as far as multiplication or division, then I got 3 sig figs to work with. Does that make sense?
Yes. Okay.
Okay.
Yeah.
Only if you were gonna just stop it at the math, at the subtraction or addition, and then they ask you how many sig figs, then 2 would be correct. But because you're going to the next step to multiply it, I have to mark all my digits. And I marked it on the 0 because that's how many, that's the decimal place, if you will, that I did with my first subtraction.
Okay.
That 0 kind of throws you for a loop. If that would have been like a 2, 122, and then you would have 171, and that would have been the end of it, right?
Yeah.
Yeah, and then you just did the division, you had 3 sig figs. But because it ended up with a 0, I know we teach that the zeros don't count, but we don't really get into the next step of, okay, I subtracted first, but now I'm going to divide. So I have to continue with the significant digits.
Yeah, that was the only one that really caught me off guard because that was the only one that was like the oddball out because everything else made sense.
Okay. It is. I'm surprised that they didn't explain that more. No, you guys don't have a lecture or anything in the lab, do you?
You're our lecturer, and we just get labs at us.
Okay.
Yeah, and then kind of what happens is that we kind of get the chat like for the lab, we kind of get the chapter, like the information of the chapter, but we don't really get a full detailed explanation about everything.
Really? Okay.
Yeah, that's what the that's what the
what-
lecture is for.
Does your lab instructor have an office time you can go and talk to
Yeah.
them about it? No, because
Sort of,
you
you have
can't-
to schedule one, but
well, because the labs, I'm fairly sure they're open. In other words, you can start the lab
Oh yeah.
and then leave it and come back in,
yeah,
unless they timed it. You
yeah,
can do that, right?
yeah.
Okay.
Since it's not timed.
Right. So you could, before you submit it, you could come with a list of questions and then email your instructor and say, hey, I need some Zoom. Does he do Zoom or something?
It sort of you kind of it's like you have to set a specific time frame beforehand. So
Okay. So I would run through the lab and not submit it and do the lab, and if you got any questions,
yeah,
make a list of the questions and then get back with him and say, hey, I got a question about this, this, and this. He or she should be able to help you. Hey, push comes to shove, bring it to me and we can work it through.
yeah,
Yeah, it says with that one, if you did that, it on like bigfigcalculator.net, whatever, it shows that it's only 2 sig figs. That's why I was like, wait, something's not right. She gave us a hint. This is not. Wait.
yeah,
Well, you should send it to her and say, hey, this one you need to explain a little bit better. I understand the hint. Well, you don't understand the hint, maybe that way. And I think a different, I'll make note of this because I will send it for my end. There's a little bit confusion that maybe a little bit more needs to be explained. We talk a lot about sig figs when you add, subtract, multiply, and divide, but they don't give us time to talk about what happens if you multiply and subtract and add first, and then you divide. And the general rule is you mark where you would truncate that number if you add and subtract, and then go on to the division and the multiplication with that mark, like I did with the 149.5. If you subtract, you don't want to truncate because if I take that number 149.5 and round it up to 149, which we normally do, and then do the division, my number would be a little bit, the propagation of the error would increase because you're truncating it and then you're doing some more math to it. So when you add and subtract, you keep all the numbers, regardless of how many numbers the calculator gives you, but you mark where you would truncate it if you were going to present that answer as a subtraction or addition. And so if I was going to truncate that example of 150 minus 1.5, I would truncate it at the 9, okay? Because the 150 has no decimal places. So my answer should have no decimal places, okay? But because I know that I'm going to take that number and divide it, I have to mark that position. So that tells me that I have 3 sig figs to work with on the next step. Okay, so when you took your number, 293 minus 123, you marked as 0 because that would be the position that I would leave my answer at. But I'm taking it one more step, I'm going to divide. So therefore that marks how many sig figs I have in the next step. Does
Okay.
that make sense?
Yeah.
Okay. And that's why the answer should have 3 sig figs, because you took 3 sig figs and divided by 3 sig figs. And what should have been explained was, yes, if I presented the answer as 170, that only has 2 sig figs. But I got that number from my subtraction, and therefore I had to mark the position where I would leave my answer at, because I'm going to take that number and then I'm take it to one more mathematical function, which is divide and subtract. I mean, divide or multiply, in this case, divide. Okay, so in this scenario here, where I got 148.85, then that tells me that mark says I got 3 sig figs in the numerator and 2 in the denominator, okay? And therefore my answer should have no more than 2 sig figs, okay? If that number in the denominator was 1.54832, then my answer would have no more than 3 sig figs, because my numerator is marked at the 3 sig fig position. Does that?
Yeah.
Let me do it. Okay.
So since it was marked at the 8, then
Yes.
that's what.
Right. So if I would have had, instead of 1.5468789, okay, that was my next math function. That 8 was marked, carrying that mark all the way through, okay. And then my answer would only have 3 sig figs in that example. In the other example, divided by 1.5, it would only have 2 sig figs.
Okay. Thank you so much.
Okay, is it clear as mud now?
Yes.
Yeah, it does.
Okay,
right.
well,
You have a good
hopefully
one.
it clears it up. So just remember, when you add and subtract, and you know you're going to divide or multiply with that answer you got from your addition subtraction,
Mhm.
mark where you would truncate that number. Okay,
Okay.
just mark it. Keep all the numbers, because you don't want to truncate it and then divide the next step, because you propagate the error. So mark, like I did here at 148.8, mark the 8. And that doesn't, all that tells you now that you've got 3 sig figs to work with for the division step.
Okay.
Okay?
All right. Thank
All
you
right.
so much.
No problem. You guys take care. I'll see you,
Tuesday.
next week. All right.
Have a good one.
Good luck with the s'mores. Is that what I heard you say? You're making s'mores?
No, those Pockies.
Oh, Pockies. I got you. All right. All right. We'll see you guys.
Yeah.